Welcome to this deep dive where we look into the latest research and pull out the key insights for you.
Today we're digging into a pretty interesting paper. It's called BitNet v2, Native 4-bit Activations with Hadamard Transformation for 1-bit LLMs.
Right, so it's all about making these big language models, LLMs, more efficient. And the focus is on using lower bits for activations.
Exactly. There's this persistent challenge with 1-bit LLMs. Getting the activations down to really low bit widths is tough.
Why is that so hard?
It comes down to these things called activation outliers, sort of extreme values pop up in the calculations.
And those outliers make it difficult to compress the activation data without losing important information.
Precisely. It complicates the quantization process quite a bit.
Okay, so our mission today is to figure out how BitNet v2 deals with these outliers to actually use native 4-bit activations. This sounds like it could be a significant step for efficiency.
It really could be. They even reference Feynman's plenty of room at the bottom, hinting at this move towards smaller, more efficient computation.
Love that connection. So let's start maybe with the basics. What are these 1-bit LLMs and why the push towards them?
Well, the idea is efficiency. Think about models like BitNet B1.58, which was kind of a pioneer here. It used 1.58-bit weights, which drastically cut down on memory needed, inference latency, energy consumption. Really big savings.
Okay, so BitNet B1.58 tackled the weights, making them super low bit, but you mentioned a bottleneck remained.
Yes, that's the key point the BitNet v2 paper picks up on. While B1.58 had those tiny weights, it still relied on 8-bit activations.
Ah, so the weights were efficient, but the activation calculations weren't fully optimized for, say, hardware that can handle 4-bit math natively.
Exactly. You couldn't get the full benefit, especially for computation. The limitations sort of shifted.
And getting those activations down to 4-bit, that's about maximizing how well the hardware is used, especially for things like batched inference.
Right. Batched inference, handling lots of requests at once, really benefits from dense, uniform, low-bit computations. 8-bit activations were holding that back.
So tell us more about these activation outliers. Where do they typically show up?
It's interesting. The inputs to the main blocks, like attention and the feed-forward networks, they often have distributions that are, somewhat Gaussian-like, easier to quantize.
Okay, so the inputs are relatively well behaved.
But the intermediate states, like the outputs inside those blocks before the final projection, that's where you see these significant outliers, very spiky distributions.
Making it tough to just squash everything down to 4 bits without losing fidelity.
Yeah. The paper mentions a predecessor, BitNet A4.8. It tried using 4-bit inputs, but still needed 8-bit for these intermediate states, and they had to be sparse.
Which isn't ideal for batched inference. You said dense is better there.
Generally, yes. Dense computations tend to be more hardware-friendly for parallel processing.
Okay, so enter BitNet v2. What's their solution? What's the core innovation?
Their big idea is a new linear layer they call H-BitLinear.
H-BitLinear.
Yeah. It replaces some standard projection layers, specifically the output projection in attention, often called WOA, and the down projection in the feed-forward network, or WIDO.
And the H stands for Hadamard, I assume, as in the Hadamard transformation.
You got it. The Hadamard transformation is the secret sauce here.
Okay, so what does this transformation actually do to the activations?
It's applied right before they quantize the activations. Its main job is to take those spiky, outlier-prone intermediate state distributions,
The problematic ones.
and reshape them. It makes them look much more like a smooth Gaussian bell curve. It basically smears out the peaks and reduces the impact of the outliers.
Interesting. So it preconditions the data, making it easier to quantize accurately down to 4 bits?
That's the idea. The paper has figures showing this smoothing effect quite clearly. It tames those distributions.
And is this Hadamard transform computationally expensive?
They mention using a fast algorithm, the fast Hadamard transform. It keeps the complexity relatively low, something like O(n) log n. So it's manageable.
Got it. So H-BitLinear uses this transform. What about the actual quantization methods? How do they quantize weights and activations in BitNet v2?
Okay, for the weights, they stick to what worked before. Quantizing them to ternary values, Monaco 1, 0, or 1. They use a per tensor abs mean function for that.
So still very low bit weights. And the activations.
That's where the split happens. For 8-bit activations, which they still use sometimes during training or comparison, they use a per token abs max method. But for the target 4-bit activations, they use a per-token abs mean quantization. Both methods involve scaling factors, gamma and beta.
And the H-BitLinear layer combines the ternary weights, the Hadamard transformed input, and this 4-bit activation quantization.
Yes, the math in the paper, equation 7, shows the full picture. It includes layer normalization before the Hadamard transform too.
Okay, that makes sense structurally.
Yeah.
What about training these models? It sounds complex.
It's a multi-stage process. They first train the model from scratch using the 1.58-bit weights, but with 8-bit activations. Standard practice almost.
Right. Get a baseline model working.
Then they continue training, but switch most linear layers, not the input-output embeddings, to use the 4-bit activation quantization, incorporating that H-BitLinear layer.
And how do they handle gradients with these non-differentiable quantization steps?
They use the straight-through estimator, or STE. It's a common technique to approximate gradients in these scenarios, and they use mixed precision during training.
Does the Hadamard transform play a role in the backward pass too?
It does. They mention applying it to the gradients as well during backpropagation.
Okay, training sounds involved. Let's get to the results. Did it actually work? How did BitNet v2 perform?
The results look quite promising, according to their experiments. First, comparing BitNet v2 using 8-bit activations against the older BitNet b1.58.
Yeah.
They found BitNet v2 performed comparably, or sometimes even slightly better, across various model sizes, 400 million up to 7 billion parameters. This was measured by perplexity and accuracy on downstream tasks.
So the new structure itself, even without 4-bit activations yet, is solid.
Seems so. Now the crucial test, enabling the native 4-bit activations.
And
They showed it works with minimal performance degradation. Its perplexity was similar to that BitNet A4.8 model we mentioned earlier.
But BitNet A4.8 had those sparse 8-bit intermediate states, right?
Correct. And importantly, for the larger 3B and 7B models, BitNet v2 with dense 4-bit activations actually outperformed BitNet A4.8 on the downstream task accuracy benchmarks.
Okay, that's a significant finding. Dense 4-bit activations beating the previous sparse approach.
And those figures we mentioned visually confirm why the Hadamard transform really does seem to make the activations more quantization-friendly.
Did they look at quantizing other parts, like the attention mechanism?
Yes, briefly. They experimented with low-bit key-value caches, the KV cache.
What did they find there?
A pretty interesting result. For the 3B and 7B models, using just a 3-bit KV cache gave accuracy comparable to using a full precision cache. That could mean further memory savings during inference.
Wow, okay. How does this whole BitNet v2 approach compare to just taking a pre-trained model and quantizing it afterwards, post-training quantization?
They did that comparison, too, against methods like SpinQuant and QuarRot.
And BitNet v2.
BitNet v2, with 4-bit activations, significantly outperformed these post-training methods in both perplexity and accuracy, even after they tried to tweak the baselines to give them a better shot.
So training with quantization awareness from the start using their method seems superior.
Their results strongly suggest that, yes.
Did they do any tests to isolate the effect of the Hadamard transform? Like what happens if you remove it?
They did an ablation study. Removing the Hadamard transform caused the model training to diverge. It just didn't work.
So it's absolutely essential.
It seems critical for enabling stable training with these low-bit activations. Interestingly, they also found applying it just to the activations, not the weights, was sufficient.
Okay, good to know. So let's wrap this up. What's the main headline from this BitNet v2 paper?
The big takeaway is that BitNet v2, mainly through this H-BitLinear layer using the Hadamard transform, successfully enables native 4-bit activations in 1-bit LLMs.
And it does so while maintaining performance comparable or even better than previous approaches, opening the door for potentially large gains in computational efficiency.
That's the core finding. It tackles that activation outlier problem in a novel way, allowing these models to better leverage hardware designed for low-bit arithmetic, especially for batched inference.
So for listeners, this means we're getting closer to LLMs that are, well, cheaper to run, faster, and maybe more accessible on different kinds of devices.
That's the potential, yes. More efficient AI.
Great stuff. A really interesting mechanism with that Hadamard transform. Thanks for walking us through this deep dive.
My pleasure.
And for you listening, perhaps a final thought. If we could make these powerful models run efficiently with such low-bit activations, how might that change where and how AI gets deployed? Think about edge devices, energy constraints. What new possibilities open up when the computational cost drops so significantly? Something to consider.